Hello, everyone. We are the Gel Polymer Electrolytes group, and presenting will be myself, Adam, Connor, and Nick. Now, the motivations for this project are pretty much centered on growing renewable energy sources. So, if you'll look, I took this slide from Exxon's 20-year energy outlook that Dr. Robert Crane gave us in Dr. Epling's class. And if you'll look at every single region, the yellow and the blue are going to show significant increases over the next 20 years. And those are renewable energies. And renewable energies need ways of storing energy. They need batteries. So today we have essentially two different kinds of batteries. So we have batteries with a liquid electrolyte solution and solid electrolyte solution. Now, both of these have their different hazards, and there's a lot of safety concerns raised with both of them. So while the demand for batteries is rising, and we're really going to need to up the production in the next 20 years, we're motivated to find safer battery solutions, and we're going to do that using gel polymer electrolytes. Now, just to demonstrate to you guys areas where these batteries are having trouble, I couldn't find exact numbers on how many battery failures there are every year, but I was able to find this table on battery failures that got a lot of media attention over the past 20 years or so. And if you'll notice, there's a couple of them start popping up with handheld mobile devices. And then here there's a large section where the Model S starts having big battery problems. And if we're going to switch to electric vehicles in the coming century, that's a big thing. We have to really start getting a hold on that. And even down here, they're starting to see battery fires in large grid connected systems, which would be the first place where we really start seeing large scale storage capacity. So we're very motivated to have gel polymer electrolytes be in a safe place.
So as you probably already know, electrolytes are very important for electrochemical applications. So a liquid electrolyte is composed of a liquid solvent that serves as a medium for ion transport and a soluble salt that serves as a source of ions. For a lithium-ion battery like pictured on the right, that soluble salt will probably be a lithium salt. Now the solvent is usually an organic solvent and is carbonate-based. And we choose a liquid electrolyte over other types of electrolytes because we can get really high ion mobility and thus greater ionic conductivity. So there are of course some problems associated with liquid electrolytes. One of those problems is that it's actually a liquid, so it can leak. And the electrolytes are often flammable. And combined with that leakage aspect, that can be very dangerous. Another thing to consider is dendritic growth. So that's when these material offshoots from the anode grow over charge and discharge cycles of a battery. And those offshoots can break off and cause short circuiting, which of course combined with that flammability aspect will cause the battery to explode. And that's exactly what happened with Samsung batteries.
In order to address some of the safety concerns and operational limitations of liquid electrolytes, scientists and engineers have developed materials called gel polymer electrolytes, or GPEs, which are polymer networks that contain highly conductive electrolytes. They are made by cross-linking either physically or chemically linear polymer chains. In this photo to the right, you have linear PEO polymer that is cross-linked chemically with UV light to make the physical or chemically cross-linked polymer network. Some common polymer hosts include PEO, which is in this image, PMMA, PVDF, and PAN. The great thing about GPEs is that they can have the cohesive properties of solids and the diffusive properties of liquids.
So in regards to preparing our GPE, we actually need to start with a precursor solution that contains our polymer, our solvent, and our salt. Now, in order to get good mechanical properties and conductivity of our GPE, we want that GPE to be homogeneous, and that requires our precursor solution to be homogeneous. This is where Flory-Huggins theory comes back into play. So we want good mixing, so we need a negative delta G of mixing, and we also want a chi parameter that's less than 0.5. So we're really more concerned with the enthalpic contribution to the chi parameter here, which can be estimated using the solubility parameter approach. And you might be thinking that we want a very small difference in these parameters, but we actually don't for a GPE, and that's because too good of mixing actually creates a very viscous polymer, gel polymer electrolyte that won't be able to stand on its own. And so we actually want that difference to be associated with this design factor xi that you can see down in the bottom right. and that's really chosen based on the polymer system. Now, it's also important to consider gelation theory. So we are working with a gel, which is a three-dimensional polymer network that has properties that are in between solids and liquids. And for gel polymer electrolytes, we can use either physical gels or chemical gels. And so a physical gel uses these physical interactions that you can see described by this entanglement network. So we have junction zones on the bottom left and fringe micelles on the right. I'm not going to get too much into that, but what's important to note is that physical gels are reversible, so they can be basically changed with heat. And that's a lot different than chemical gels, which are covalently cross-linked to form these junction points you can see right here, which are irreversible as they're basically chemical bonds. So we can actually use Carruthers equation and statistical theory here for a chemical gel to predict at what conversion of our monomers will we achieve a true gel. Now, another thing to consider is plasticizers, which are a type of polymer additive that modify the properties of the polymer. And in general, you can see right here what adding a plasticizer does. It really changes the properties of a polymer to be a lot more flexible and have elasticity. But for GPEs, plasticizers are actually the solvent component of our liquid electrolyte. So plasticizer is now our new fancy word for a solvent. And what it does is when we add this plasticizer to a solid polymer electrolyte, we cause that polymer host matrix to swell, and we get improved ionic mobility. So you can see some common plasticizers for GPEs right here. Now, it's important to discuss actual ion transport phenomena. So ion transport is a diffusive process like any other molecule. So a high concentration will cause ions to move to a low concentration. And in order to help out with that, we want our plasticizer to contain or have a high dielectric constant and low viscosity. Both of those things really help out with ion mobility. And something that's important to note is GPEs are typically porous. So you can actually see this picture right here, all these little pores. And because of that, there's actually two modes of transport that occur in the GPAs. So there's a fast diffusion pathway, and that happens through these cavities within the polymer where there's basically just some solution sitting that hasn't actually absorbed into the polymer itself. And that's fast, of course, because that's basically like a normal liquid electrolyte region. And then the more dominant pathway is the slow diffusion pathway, which occurs through these swollen polymer domains that you can see up here in this picture on the right. So on the left, we basically have a solid polymer electrolyte with very few amorphous domains. And once we add our plasticizer, we get growth in those domains and frequency. So we have more domains and larger domains that are able to form this network of amorphous domains that allow for ionic conduction. And it's pretty well documented that ions will only diffuse through these amorphous regions of a polymer. Now, it's also important to consider the conductivity of both our polymer and solvent. So conductivity is directly related to that ion mobility we just discussed. So we can get more mobile ions, we have better conductivity. And GPEs have conductivities that are intermediate to both liquid electrolytes and polymer electrolytes. And that's really pretty apparent over with this graph here. So as we move kind of in between both of those, we get into this hybrid electrolyte region where we have intermediate conductivity properties. Another thing to consider is that when we increase the temperature, we will get higher conductivity, and that's for both the polymer and the solvent. And there are two mechanisms behind that. When we increase our temperature, we decrease the solvent or plasticizer's viscosity. We also get a higher solubility, so that really helps the ions dissolve into the solution and kind of move through and diffuse. For the polymer, when we increase temperature, we get more amorphous character and therefore more of those amorphous regions that I just discussed. And as we know, when we have amorphous regions, we're able to, those ions are able to better move through the polymer. So something that's good to consider is if the Arrhenius equation actually works for both the polymer and just the general solution part. This is pretty well documented that this works well for a solution, but it's a little bit different for a polymer, as you'll see. Up here at the top, it's actually a lot more complex. You can see a modified form of the Arrhenius relationship. And what actually happens is that the Arrhenius relationship works well in these regions where you kind of see this linear behavior of the conductivity with temperature. But you have this really sharp jump up here as you increase temperature. And part of that has to do with the existence of those amorphous regions like I talked about. So when you increase temperature, you get more amorphous regions. And in those amorphous regions, you get something called dynamic segmental motion. And that basically means that the polymer chains can move past each other a bit more than over in this more crystalline region. So in the crystalline region, you're really bound to this ion hopping mechanism where the ions can really only jump from vacant sites through the polymer. But when you have this segmental motion, the polymer molecules themselves can actually help carry the ions around, and that really contributes to ion transport and yields a higher conductivity.
In the next few slides, I'm going to go over some of the main GPE properties and how scientists have enabled those properties in GPEs. The first one is thermal stability, and this is really important because GPEs are used in a lot of applications where the temperature is really, really hot. And sometimes GPEs can degrade. This is the case for PEO, which has a melting point of around 65 degrees Celsius, which is really low. The way that GPEs can be made to have an increased thermal stability is through adding a copolymer that has a high thermal stability on its own, like PVDF. The Su et al. Paper, where this figure is from, they added PVDF, a copolymer of PVDF and PAN to their PEO, and this increased their thermal stability a lot. As you can see here, it increased it to about 400 degrees Celsius. The next GPE property that's really important is mechanical strength, and this is because GPEs are used in a lot of applications where there's a lot of jostling around, and the GPEs need to be freestanding and be able to take some of those mechanical forces. The way that GPEs can achieve this strength is through adding inorganic ceramic fillers like titanium dioxide, aluminum dioxide, and silicon dioxide. And this is what Li et al. Did in 2015. They added silicon dioxide to PVDF, which increased their mechanical strength. That's what you can see here in this figure. You have the pure PVDF, a stress versus strain curve of pure PVDF in black with a tensile strength of about 13. And you have the red here, which is PVDF with silicon dioxide added to it, which has a tensile strength of about 26. So it increased it twofold. The third GPE property that's really important is ionic conductivity. Ionic conductivity is the ability of an electrolyte solution to conduct electricity, which is really important for gel polymer electrolytes, of course. The units of ionic conductivity are Siemens per centimeter, S per cm. And for reference, liquid electrolytes have an ionic conductivity of 10 to the minus 4 to 10 to the minus 2 Siemens per centimeter. GPEs tend to have a lot lower conductivities, but the way that scientists have figured out a way of increasing the ionic conductivity is by adding, again, inorganic fillers. This time, Lu et al. Used titanium dioxide, and this is what this figure is from a 2003 paper that they published. And you can see here that as you increase the titanium dioxide up to about 10%, the ionic conductivity of their polymer increased as well, about tenfold. The fourth property that is really important for GPEs to have is non-flammability. This is because current liquid electrolytes are really flammable, and the applications that they're used in have very high temperatures, and as the electricity is flown through them, it can spark and cause fires. And the way that GPEs can be non-flammable is by incorporating ionic liquids. And these are basically salts in the liquid state. They have a very low vapor pressure because of this. Li and Kim in 2013 showed that when you add ionic liquid monomers and you either polymerize them or don't polymerize them, they can decrease the flammability as you increase the monomer content.
So Adam told us a little bit about the properties of GPEs, and we just want to go over them real quick. So for a good gel polymer electrolyte, we need to have a good ionic conductivity, high cation mobility through the matrix. The polymer needs to be porous and be able to easily take in the electrolyte. It needs a high electrochemical stability. It needs a high thermal and chemical stability. So when we're looking to design these, we need to find monomers that will fill all these properties. So generally what this leads to is it accumulates in a polymer having a carbon-based backbone and having heteroatoms that are chemically and electrochemically stable. So like oxygen and nitrogens are pretty good. And we want these because they're polar and they can help transport ions through the solution. So listed below here is a diagram that shows how lithium plus ion, for example, can get transported through gel polymer electrolyte. So these circles here are polar heteroatoms or polar side groups, and what they'll do is they'll surround an ion, and it'll get passed down the chain like so. Now, what monomers really fit the descriptions, and what polymers can we make out of these? Well, most commonly are polyethers and polynitриles. And the reason why is, like I said in the previous slide, they have these heteroatoms in the backbone, and they have really good flexibility, like here, or the nitrogen here. They're flexible, so they can, move like these chains do over here. They can swarm it. They're not rigid, and they'll be conducive to ion transport. So how do we actually make one now that we've decided what we want our basic outlet to be? So this is the most general form that I found. It's making a polyether polymer, gel polymer electrolyte. What they'll do is they'll start with ethylene glycol or some derivative of this, and they'll use a method called atom transfer radical polymerization. And shown below is this method. So what they'll do is they'll start the polymerization process. They'll use this initiator right here, and this will form a radical, and the radical will attack the oxygen, and the bromine will leave, and it'll bond with this group here. And then what will happen is this bromine will react the same way with another oxygen-hydrogen group. And so you can sort of see how this polymer starts to form. So once the polymer chain forms, what they'll do is they'll mix it with divinyl benzene, or DVB, which is depicted here. And it'll react with that, and it'll form this star shape here. Now, I call this like an epicenter, and there'll be multiple epicenters throughout the polymer electrolyte. So, this chain will end in one, this chain will end in one, this chain will connect to another, and so on and so forth. And what this does is it allows for, really highly, a large network of this polymer to form, and it's very porous. And these chains, the key part is that these chains are really flexible. They can bend and move around polar ions. So there are lots of other kinds of polymerization. I have a few listed here. There's a lot being researched. Truth be told, we don't really have time to go into every single way to make a gel polymer electrolyte. These are fairly new technology, like I said, and there's just so many. These are just a few that I found in the readings. But I just want, the purpose of this slide is just to let everyone know that radical atom transfer radical polymerization is not the only way they make it. It's just the most common. So now we have how the polymer forms. We need to figure out how we make it a gel polymer electrolyte. So you're going to need a solvent to do that. Now, solvents are also still being heavily researched. These are sort of, the biggest part of the research, I would say, because the solvent is what's going to dictate a lot of things like energy density and power output, and things that people generally care about when they're looking at batteries. So while we don't have like a common solvent to use, because the solvent's dependent on both the polymer and the requirements of the battery, there are some common trends in solvents. So generally they'll be organic and aprotic. They will also contain metal salts to aid in ion transfer. Generally some sort of metal oxide will fit this bill. And then the solvent will also be a plasticizer. So it'll serve to make sure that the polymer is not so rigid. And that's very important, especially when you look at polynitriles and whatnot, or even more complex polyethers. These side groups can start to make it a little bit rigid. So if that's the case, then they'll adapt the solvent to fit that.
So for moving into the applications of gel polymer electrolytes, now that we know how they're made and the applications of them, one of the first and main applications is the flexibility of them. And when we talk about this, it's generally in regards to flexibility with electronics. As being a gel, these polymers are very malleable, and that allows for the polymer to be twisted, reshaped, and molded into what is most efficient. Being a gel, it's easy to fill similarly to a liquid in between the anode and cathode and electrode. And here we have like a small little diagram that shows it and shows that it's very flexible, very bendy, but still gets the job done and the method across so that it is able to produce and hold the electric charge that we would want in a battery for a electronic device. Furthermore, with the porous shape, as we've learned from the previous sections, it makes for an excellent conductor, and it allows for the battery to have a longer life. And with the flexibility, it means that you can have a battery in many different shapes and still be able to hold the same kind of capacity that you would want regardless of it. And it was also very important to note is that with the current technology we have for the liquid polymer electrolytes, they have to be in the cylindrical that we see. Typically, like double and triple A batteries is what would be those kind. But here, with the flexibility of these electrolytes, of these gel polymer electrolytes, we're able to make it so that it's different shapes. You have electronic batteries in phones, laptops, even batteries for cars are all made with these gel polymers so that it makes it better for everybody all around. Also, we have aeration. Because of the porous structure of it, it allows for very good aeration. This is, as we've seen, very important for with the temperature control. When you're able to aerate something, it allows them to be cooler for longer, and even in hotter temperatures, be able to keep the cool temperature so that they do not get to overheat, they do not explode, and they do not reach the critical temperatures that we want to make sure that they're avoiding. This can be used for solar panels, for batteries in cars, for batteries in all kinds of electronic devices. Because like taking it, when they absorb it, you have all the energy coming in. And then with the battery and the charges flowing through it, they're still allowed and able to use the aeration from the pore structure to get cool air coming in and keep the hot air flowing out. And with this, because of the temperature, it works to prevent the degrading of this polymer. And finally, as we move into an economic overview, one of the things to point out is similarly to what I was talking about with the flexibility. Here we see your stereotypical AA battery that is a liquid electrolyte. So it's like stuck in that shape because of the current technology we have. Well, if you look at a phone or similarly to computer batteries and other batteries, we are able to make it so that they are different shapes and sizes so that they can fit into areas that we might not be able to have just a set cylinder fit into. They're cheaper and easier to produce and longer lasting than other batteries that would be able to fill that size. And currently, they do hold a place in the market, again, as being stated, for car batteries, phone batteries, and the same stuff that I've been saying. It makes it so it's very effective and able to help with the market. And going forwards, they're working on advanced geopolymer electrolytes, which are basically the same thing, but using technology that we're not able to get into in this time frame to make it so that they are more effective and can hold charges for even longer, up to current statistics show that they can, with the advanced technology and using another synthesis to upgrade the polymer, they can currently hold a hold a charge for approximately 50% longer than what is currently being used.